Right, we are talking about so-called Brinkmann solutions, also known as PP waves. The general form of the metric is this. There are coordinates x1, x2, u, and v. dx1 squared, dx2 squared, minus 2 du dv. That would be just Minkowski spacetime in double null coordinates. So the u coordinate would be this. The v coordinate would be this, and x1 and x2 are perpendicular to the board. And then we modify this by introducing a function which depends on x1, x2, and u, not on v, times du squared, which means that v is still a light-like coordinate, but u in general is not. Yeah? U is only light-like at points where this is 0. Where this is positive, it is space-like. Where this is negative, it is light-like. So the light cone at each point touches the v lines, but where it is on the other side, this depends on the function h. In the space perpendicular to the board, everything is trivial. Yeah? So if I set u equal v equal constant, then I am in a plane perpendicular to the board, and this is just the Euclidean plane, parameterized by x1 and x2. So there are planes, and there are these light-like rays. So for this reason, these spacetimes are called plane-fronted gravitational waves with parallel rays, PP waves for short. Okay, and we have already evaluated Einstein's field equation. So if we have, maybe I should say one word more. So this function h here, this depends on x1, x2, and in particular on u. So if I plot this here in this direction, so if I plot this function here, so this would be h for fixed x1, fixed x2 as a function of u goes in this direction, then you see that it determines the profile of the wave. Yeah? And because everything is translation invariant in the v direction, we have shown this in the last worksheet, we have shown that this vector field d by dv is an absolute parallel vector field. So in particular, it is the killing vector field. So in this direction, I have a symmetry. So this profile doesn't change when the wave propagates in the v direction. Yeah? So if I'm standing at one particular point, so if this is my world line, then this wave sweeps over me, and then I see this profile as a function of time. So in this sense, u plays the role of a time coordinate. But d by du may be time-like or space-like depending on the sign of h. Okay, and then I've calculated the Christoffel symbols. It was very simple. The metric is actually a metric which can be handled very easily. Has many symmetries. All the calculations are quite simple. And from the Christoffel symbols, we could evaluate the vacuum field equation, and we have seen that it is, or I've just told you, I haven't calculated it in detail, that this is just the Laplace equation for h as a function of x1 and x2. The capital indices take values 1 and 2. So you see, this is a trace of the Hessian, right? The trace of the Hessian of h must be 0. This means one eigenvalue must be positive, one eigenvalue must be negative, right? And they must be equal in modulus. So you see, in one spatial direction, if you have in one spatial direction defocusing, yeah, so the second derivative pulls the thing apart, then in the other direction, it pushes things together. So we have this typical behavior of gravitational waves that that a certain trace must be equal to 0. So in this case, it's this equation. I'm not sure if I mentioned this last time. There's a very important property of this equation. It's a linear equation. And this should come as a surprise, right? Because in general, Einstein's field equation is not a linear equation. It's a nonlinear differential equation. But with this particular ansatz, it boils down to a linear equation for h. So for this particular type of gravitational waves, the superposition principle is still true. Yeah? In general, it's not true for gravitational waves. It's a full theory if we go beyond the linearized theory. But with this ansatz, it is still true. So if someone has found a function h1 which satisfies this equation, someone else has found a function h2 which satisfies this equation, then we can form the metric where we insert the sum h1 plus h2, and it's again a solution. Yeah? So the superposition principle holds. This is a very important property which simplifies matters considerably if you discuss waves of this type. Okay, and then we specified, so this is the general class of PP waves or Brinkmann waves, and it's very common to consider a subclass of this where we consider a particular solution of this equation. So the differentiation is only with respect to x and x1 and x2. So as a function of u, this may be anything. Yeah? It's completely arbitrary. There's nothing, no particular condition on the dependence of u. And the simplest way of satisfying this equation is by requiring h to be of a second order in x1 and x2. Yeah? Then the Hessian would be just a constant. So we require, as a special case, we consider this situation that this is a coefficient matrix HAB, which depends only on u, and then XA, XB. And of course, then the condition R mu nu equals 0 is just the condition that the trace of this coefficient matrix must be 0. Must be 0. So if I write this as a 2 by 2 matrix, HAB, I think this was the last equation we had on the board last time. Then let's call this coefficient f plus u, and this here f cross u. Then because the trace vanishes, I must have minus f plus here. And because the matrix is symmetric, I must have x cross u here. And well, this reminds very much of what we have discussed in the linearized theory, right? So also here we have, with this particular ansatz, we have a trace-free matrix in the game. It's not harmonic in U. Yeah, in the linearized, when we discussed the linearized theory, we assumed that we had a harmonic dependence on the time. U now plays the role of a generalized time coordinate. So here it may be any dependence on U. Yeah, so the profile may be anything, not necessarily sinusoidal, but apart from this, it looks very similar to what we had in the linearized theory. Okay, let's look at the, oh, maybe I should have written this here. I calculated the geodesic equation, right? So, yeah, I think I should write this again, because I need it now. So the geodesic equation, I should have written it where I put the arrow. Yeah, so for this metric, I calculated last time the geodesic equation, and I will need this again now. So this was the first equation I know by heart. So double dot equals 0. That's simple enough. And the other one, dot means derivative with respect to a curve parameter. Affine parameterization of the geodesic. Geodesic may be time-like, space-like, or light-like. No difference. Here we are. So the second equation was v double dot is minus 1/2 duh. This is for the general form of the metric. Duh u dot squared minus dA h u dot xa dot is equal to 0. So here you read the Christoffel symbols, right? And the last equation is xa double dot minus 1/2 delta AB dBH u dot squared is 0. So this was a
equivalent sign, and v double dot is wrong.
What is wrong?
The first equivalent sign.
Oh yes, thank you. So I put everything to the left-hand side, yes. Okay, and now we can specify this to this more specific form, and then we can discuss a little bit the focusing properties. And here we can investigate the question to what extent the behavior of this wave, the effect on geodesics, is similar to what we have studied in the linearized theory. Okay, now, so this was the general form, and now I continue here. Geodesic equation with a special ansatz. Of course, the first equation, nothing changes. It is still u double dot is equal to 0. The second one becomes v double dot is minus 1/2. No, minus 1/2. U derivative of h. This is HAB prime, right? Yeah, HAB depends only on u, and I write just the prime for the derivative with respect to u. XA, XB, u dot squared, minus the AH. The AH, this is 2 times, do I have a 1/2 here? Let me see. It's a convention, of course. No, I don't have a 1/2 here. Then I get a 2 here. Let me see. I'm a little bit confused. Okay, but I think there should be a 2 now. DAH, because I have to differentiate with respect to both factors, right? So I get 2 times. It's a lower index A. So I have A, B, XB, right? I think that's it. U dot XA dot equal to 0. Okay, I will not do much with this equation. Anyway, that's not so important, but the third is important. The third equation is important. I can write this as a matrix equation now. I write this equation as a matrix equation. So then it is x1 double dot, x2 double dot. And here I have 1/2. The gradient of h with respect to b, this is just h, the matrix H, which I've written here. So this is f plus of u, f cross of u, f cross of u minus f plus of u, times xb, right? Times x1, x2. So that's the third equation. U dot squared, u dot squared. Okay? So u is a function of s, also x is a curve parameter. Also x1 and x2 are functions of s. This means derivative with respect to s, and that's the equation we have to solve. So we observe that there are 2 cases. Either the geodesic is completely contained in the surface u equal constant. U equal constant is such a hypersurface. Yeah, it's a hypersurface which is ruled by the rays, by the integral curves of V. And then these 2 equations tell how this geodesic moves in this plane, hyperplane, u equal constant. But if u is not a constant, then this equation says that it is a linear function of s. And if it is a linear function of s with a non-zero coefficient in front of s, then I can reparameterize my geodesics in an affine manner by a linear coordinate, by a linear parameter transformation, so that u becomes equal to s. So I can use u as an affine parameter. Yeah, remember, an affine parameter is defined up to affine transformations. That's where the name comes from. So I can always transform s into as plus b. Then the geodesic equation is preserved. And if u has precisely this form as a function of s, then I can use u as a particular affine parameter. For time-like ones, it will not be proper time. Yeah, it will be affinely related to proper time, but not directly equal to proper time. For light-like, it doesn't matter because all the affine parameters are undistinguishable anyway. So if I continue there, so if u double dot is not 0, so I exclude this case now. It's the geodesic is completely contained in this hyperplane u equal constant. So then we may choose u of s equal to s. Yeah? And the first equation is identically satisfied. The second equation gives me v as a function of s. And from the third equation, all the other parameters drop out. It is just a system of differential equation for x1 and x2 as a function of s. I write this again. And this is the only equation which, in essence, you have to discuss if you want to know what a gravitational wave is doing to your geodesics. So this is 1/2. So I have now set u equal to s. So I may write f plus of s. S is now the argument of the function f plus. Similarly, f cross minus f plus, you have x1 of s, x2 of s, and u dot is equal to 1. Yeah? So this has completely decoupled from the rest of the differential equations. Yeah, just the system for the functions x1 and x2 as functions of s. F plus and f cross, of course, are given. Yeah? I prescribe my profile functions, and then I have to solve this. And this tells me how the gravitational wave affects geodesics. And well, we see that now it's important that we have a linear differential equation to solve, that I can consider these two polarization states separately. Yeah, I can consider solutions where f cross is equal to 0 or where f plus is equal to 0. And then I see I have a behavior very similar to what we have studied in the linearized theory. In the first case, I have an effect only along the axis of my x1, x2 system. And in the second case, I have the effect rotated by 45 degrees. So let's consider f cross equal to 0. So we have a pure, I shouldn't say plus mode. Yeah, mode refers to something which is harmonic in time. Yeah, we say that we decompose a wave into modes when we do a Fourier decomposition. So I shouldn't say plus mode and cross mode, but these are the two polarization states. Yeah? A plus polarization and a cross polarization. These are the two states which I recognize here again. So then we see what happens to our gravitational wave. Then the thing becomes diagonal. So this is 1/2 f plus of s, x1 of s, and here I have minus x, and no dots, of course, x2 of s. So you see, if f plus is positive, then I have focusing in the x1 direction and defocusing in the x2 direction. And if f plus is negative, it's the other way around. So whenever I have a motion away from the central ray in one direction, I must have the counter-directed motion in the other direction. So it's a typical behavior which we have observed already in the linearized theory. The main difference here is that the amplitude may be arbitrarily big, and it may have any form. Yeah, the shape of this profile function is completely arbitrary. It could be sinusoidal, or you could have something, what is called a sandwich wave, yeah, that it is 0 up to a certain value of u, and also beyond a certain value of u here it is 0. Then I have Minkowski spacetime here, I have Minkowski spacetime here, and I have a wave in between, which just propagates along the V rays. Yeah, that's what one calls a sandwich wave, sandwiched between two pieces of Minkowski spacetime. That's where the name comes from. That would be another possibility, or any shape you like. Could also be negative. H can also be negative. I've drawn it in a way that it indicates that it be positive, but it's not necessary. H can also be negative.
So it needn't be a continuous function.
Oh, yeah, okay. Actually, you can discuss this also for distributional H's. Actually, this is done quite frequently, for instance, for Dirac delta-like pulses. Yeah? You have to be a little bit careful if all the operations are well defined. But because it boils down to a linear differential equation, actually you can work with distributions. Yeah? At least the traditional ones, as they were introduced by Sobolev and by Schwarz, these traditional distributions, they only work with linear differential equations. There's a very sophisticated, more general theory by a Frenchman called Colombo, but I never learned this, and I cannot say anything about this. It's awfully complicated. Then you can handle nonlinear differential equations with distributions.
But even this sandwich wave,
yeah.
Right? You say if it's 0 at the ends, then it's not continuous.
Why not? You could have something like this. It's 0 up to here, 0 up to here, and then it comes with a horizontal tangent up.
Okay,
Yeah?
Then this derivative is not continuous, right?
Well, you could have it even C infinity. You cannot have it analytic, but you can have it C infinity. Yeah? Okay. It could not be could not have a convergent Taylor expansion around this point, but it could be C infinity. All derivatives could exist.
Okay, this is enough.
Yeah. As I said, even it works for much more general functions. Yeah, even for distributions like a Dirac delta or a step function or things like that. Okay, and these gravitational wave, how is it called? Impulsive gravitational wave, it's called, if you have Dirac delta, yeah? There's a fairly big literature on this. Okay, what did I want to say? Yes, so this is a differential equation we have to solve. So this describes the behavior of geodesics if we just look at what happens in the direction transverse to the motion of the wave. Here's the x1, x2 planes. All this happens in the x1, x2 plane. And the other directions are then fixed. Yeah? If you have solved this differential equation, you give me the f plus, and if it's non-zero, also the f cross, then we solve this system of differential equations, and then we insert the solution into this equation, and we get v as a function of s. Yeah? So it tells us how the wave behaves in the direction in which the wave propagates, and the u double dot is always 0. Okay, so in this way you can study the motion of time-like geodesics. This means free particles. So you may think of dust particles. Yeah, you place them in a certain array, and then you look what the gravitational wave is doing to it. And this equation describes this. But it also works for light-like geodesics, and this is particularly interesting because it tells you how a gravitational wave focuses light. Yeah, and this is a focusing which really works for arbitrarily large amplitudes. Yeah, this is important. We have nothing like linearizations. We no assumption that something must be small. This can be huge. It can be a huge amplitude. Yeah, and then we get, as we will see in a minute, very strong focusing effects. And the first person who discussed these focusing effects was Roger Penrose. And Penrose is famous for many things. One of the things for which he is famous is that he can produce marvelous hand drawings of mathematical situations. And his hand drawing for a light cone in this space-time is one of his most famous pictures. And I couldn't resist to show this to you. So this was from a Penrose paper from '65 or so, where he considered this metric, which we have just been discussing. Actually, he considered the sandwich wave. This means a wave where the amplitude, the profile function, is different from 0 only in a finite interval, finite u interval. And he produced a hand drawing of the light cone. Oops. Okay, and here it is. Let me see if it will come up. Okay, here we are. So here you see this is a reference. The title of the paper is something like a remarkable property of gravitational waves or something like that. And what is drawn here is the future light cone of an event Q, or what is the same, the past light cone of this event R. And of course, even Penrose cannot produce four-dimensional drawings, so one of the dimensions is omitted. Yeah? And what is omitted is either x1 or x2. So we have the UV plane, and then only one of the transverse dimensions is shown. And the dimension which is shown is the one in which I have focusing. Yeah? When I have focusing in one of the spatial dimensions, I have defocusing in the other direction. This is not shown in the picture. This is the dimension which is missing. And you see? No. Oops. You see what happens? So, okay, let's look at the event R. They're up there on the left. So there is one light ray going through this event R. This is this straight line. This is an integral curve of the vector field d by dv. It's a v line. It's a light-like geodesic. This is a straight line in this coordinate picture. So this is contained in the hyperplane u equal constant. So it's one of these geodesics which we have omitted here. Yeah, because here I have assumed that u double dot is not 0. But All the other ones which issue from R into the past, all of the other ones are described by the equations which I have on the board. And you see what they are doing. They go away from the UV plane, and they can go very far away from the UV plane, and then they are focused back. They come back to the UV plane, and then they are focused into this point. And all of them are focused into this point in this 2 + 1 dimensional picture. Yeah? So all the past-oriented light rays issuing from the point R are refocused into the point U, with the exception of the single ray, which is just a straight line. So a gravitational wave, at least these particular gravitational waves, do a perfect focusing in a 2 + 1 dimensional space-time. They refocus everything into a single point. Now, if you take the other dimension into account, which is not shown in the picture, then you will see that this is actually not a point. It is a one-dimensional curve. Yeah? So the focusing is not in the way that everything goes into one point in space-time. It goes into a line in space-time. And actually, it's a parabola. So it extends to infinity in both directions away from the UV plane. And so you have focusing in one spatial direction and defocusing in the other direction. So the focus is not a point, it's a line. For this reason, this is often called astigmatic focusing. Astigmatic in Greek. Do we have a Greek here? So I think it means not point-like. Yeah? Stigma is a point, if I'm not mistaken. So it's astigmatic focusing. There's a variant of this where you do not require this Laplace equation. Then it's no longer a pure gravitational wave, but it can be interpreted as a gravitational wave and an electromagnetic wave. Yeah? So if you drop this assumption that the Laplacian is 0, you just consider arbitrary metrics of this form, then you have in general also an electromagnetic wave in the game, and then you can produce stigmatic focusing. That really everything is focused into a single point. But a pure gravitational wave cannot do this. So this was the discovery by Penrose in this paper. And he also, you see here it's written Cauchy hypersurface. Maybe I should make a remark about this. So another important property of this metric is the following. If, well, I think I mentioned this word Cauchy surface briefly earlier when we talked about wave equations and the initial value problem for wave equations. A Cauchy surface is the following. It's a surface if you give initial data for a wave equation on such a surface. It's a hypersurface, three-dimensional. Then the solution is fixed everywhere in the space-time. And not every space-time has a Cauchy surface. So you cannot always find a surface so that initial data on this hypersurface determines the solution of the wave equation everywhere. A solution where, an example where it does exist is Minkowski space-time, of course. T equal constant is a Cauchy surface. Yeah, if you give initial data on this hypersurface, then the solution to the wave equation is fixed everywhere. And the formal definition of a Cauchy surface, the criterion which must be satisfied in order to get a well-posed initial value problem globally, is that every causal curve must intersect this hypersurface precisely once. Every time-like and also every light-like curve must intersect it precisely once. If there is one such causal curve which does not intersect the surface, it's not a Cauchy surface. And if there is one which intersects twice, then it's also not a Cauchy surface. So here's another example. In Minkowski space, you could also consider the hyperboloid. Yeah, this is a light cone, and now you fit a hyperboloid inside the light cone. This is also a space-like hypersurface. It's everywhere space-like, but it's not a Cauchy hypersurface, because here I have a time-like curve which never meets this surface. Yeah? So Minkowski spacetime does admit Cauchy hypersurfaces, but not every complete space-like hypersurface is a Cauchy hypersurface. And now what Penrose discovered was that these gravitational wave spacetimes do not admit a Cauchy surface. So if you want to discuss an initial value problem for the wave equation in this spacetime, yeah, not the wave equation for the gravitational waves which we have constructed, but now say an electromagnetic wave. Hey, you want to give initial data for an electromagnetic wave, for instance, then it doesn't work globally. And it's from the picture, it's quite obvious that it cannot work. So let's assume there is a Cauchy hypersurface passing through this event Q. Then this must be a hypersurface which is hit by every, or met by every causal curve precisely once. But you see, If you just consider a straight hypersurface, then there are light-like curves which intersect it twice. Yeah? So obviously, if I use a straight one, then there are light-like, even light-like geodesics who are intersected twice. So you have to avoid these light-like geodesics, so you try to curve it downwards, but then this light-like geodesic never reaches the hypersurface. So just geometrically from the picture, you can easily see that the space-time does not have a Cauchy hypersurface. And this was kind of a surprise, because it is topologically trivial. There are no handles, no holes or something like that. The topology is R4. Yeah, the four coordinates, x1, x2, u, and v, run over R4. No topological subtleties. Yeah? And the space-time is geodesically complete. No geodesic reaches the boundary at a finite affine parameter. We can check this fairly easily. So I think until this time it was thought that, or maybe implicitly assumed, that every topologically trivial and geodesically complete spacetime would be globally hyperbolic, would admit a Cauchy hypersurface. But this was an example that this is not true. So this was also an interesting result from this Penrose paper. Now you have to imagine the ingenuity Penrose had to put into this work. This was 1965, so computer visualization was practically non-existent at this time. Yeah? So what Penrose had to do was he had to look at a system of differential equations and then translate this system of equations into a picture. Yeah? And that's what he came up with. So this was a remarkable property, a remarkable achievement. Of course, nowadays it's very easy for us. We have computer programs like Mathematica, and we can produce light cones like this with a computer. And I felt tempted to check if Sir Roger was correct with this picture. So I produced the light cone for this. Oh, this is the wrong one. This is what I wanted to show you. For such a sandwich space-time, and you see Sir Roger was perfectly right. Yeah, it's exactly what he had drawn. So you see again, here's the light-like geodesics which move away from the surface from the UV surface, then turn back, go fairly far up, and then come down and are refocused into this point. So this is this effect that the light rays which move away from the starting point, that they are bent backwards by the gravitational wave in this spatial direction. And I emphasize again, the amplitude may be arbitrarily big. Yeah, so this really extends in this direction, arbitrarily far away. So in the linearized theory, of course, you could only discuss a small neighborhood of this central ray, which goes down to the focal point. But here you can do it in the full nonlinear theory, as far away as you like. And I've said several times that in this picture, one of the spatial dimensions is missing. You have to keep it in your mind. And in this missing dimension, you have actually defocusing. So if you want to produce a picture where you see both the focusing and the defocusing effect, then you have to omit one of the other dimensions. And obviously, the dimension which you would then omit is the upward dimension, yeah, which is a time dimension. So we produce everything. We project everything into the 3 space, where we project along the integral curves of v plus u. And what you then get is this here. So this is now purely spatial. So you have all the light rays issuing from this point. Of course, they issue in all spatial directions. I have drawn only a pencil, a light ray with a certain opening angle going to the right. And you see in one spatial direction, you have the focusing. This is the vertical direction in this picture. There everything is focused. But in the direction perpendicular to this, you have defocusing. There everything is pushed apart. So that's what a gravitational wave is doing with light rays, which are issuing from this point on the left. And up to the first focal line, it's a focal line, not a focal point. Up to the first focal line, this is universal, this property. It's the same for all kind of profile functions. what happens then? If there is, after this focal line has been crossed, if then there is a second focal line or a third and so on, this depends on the special form of the profile function. So this is not universal, but there is this first focusing and defocusing effect. This is universal for all profile functions. So even if you have a very weak and very short-lived sandwich wave, yeah, so only on a very small u interval you have this different from 0, you have this profile functions, then you already have this focusing effect. You have it always. Actually, this was a case discussed in some detail in the Penrose paper. So we considered weak sandwich waves. Yeah, so only a short interval where the profile functions are different from 0, and then he discussed this focusing property. Okay, so you see, this is of course something which you cannot discuss in the linearized theory. Yeah, and you couldn't make any statements about focusing properties of gravitational waves in the linearized theory. So you really need the full theory in order to discuss this. And that's the reason why I think this is instructive, and one should have a look at these exact solutions. Of course, for all practical purposes, for gravitational waves which actually arrive here on Earth from merging black holes or whatever, of course, the linearized theory is sufficient. Yeah, so you wouldn't need these equations which are true for high amplitudes. Okay, so much for the Brinkmann solutions for the plane-fronted gravitational waves with parallel rays. And now let me see, I have 3/4 of an hour or so. I will use this for another class of gravitational waves, and these are the things which are usually called Einstein-Rosen waves, but actually they were found by Guido Beck already 12 years before Einstein and Rosen. Should we switch this off? Let me see if I can manage to do this. Oops. Thank you. Sure.
So can we obtain from let's say from these exact solutions that we have the linearized equations that we had earlier?
Yes, of course. Yes. Yes. Well, we have here solved the exact equation r mu nu equals 0, right? So this. Let me see. It could, I think in this particular case all the nonlinear terms drop out, right? Yes, I think it should be this way, yes. So in general, this expression, r mu nu, contains terms which are nonlinear in the deviation from Minkowski spacetime. This was this term in this case, and in its derivatives. But in this particular case, it contains only linear terms. So actually there is no difference between the linearized theory and the full theory in this case. So what we have from the linearized theory, where of course we only know that it is valid within the domain of validity of the linearized theory. So if this perturbation is small, yeah. So what we have from this theory also holds in the full theory. But this could not be anticipated, of course. Yeah, you really have to go through the whole formalism, so that this general features are also true for the nonlinear waves. Yeah, it must be this way, of course. Yeah. So in this particular case, for this particular ansatz, this expression is linear in H and its derivatives. Yeah. Which is a special case. In general, it would not be linear in the perturbations. Okay, so these were linear. These were plane waves. Yeah. So the wavefronts were these these surfaces u equal constant and v equal constant. These surfaces parameterized by x1 and x2. And these things which I really think one should call Beck Einstein-Rosen waves. these things, or solutions, let's say. They are cylindrical waves. Yeah. So what did Guido Beck do in 25, I think? Was it the same year as Brinkmann? I think so. I think Brinkmann was also 25, but they didn't know of each other. So where are we? Oops. 113, 14. Here we are. Yes, 25. So this was Zeitschrift für Physik. Uh, 25. And Einstein and Rosen, I say a little bit about their work later. This was 12 years later, 37. So at the time when Einstein was in Princeton. And Rosen was his collaborator at this time. I think Rosen was the only native US American with whom Einstein ever worked in Princeton. All the other ones were immigrants, like he himself was. Nathan Rosen was a native US American, came from New York, and he worked for a couple of years with Einstein. There's one famous paper where they collaborated. I think everybody has heard about this. There was a third person involved. Who knows who was the third? Podolsky. Yeah, he came from Russia, Boris Podolsky. And this was a famous Einstein-Rosen-Podolsky paradoxon paper, where they questioned the probability interpretation of quantum mechanics. And this paper is still discussed today. And people have still not a common opinion on this. So this work on gravitational waves by Einstein and Rosen is not quite as famous as this Einstein-Rosen-Podolsky paper, but it also has an interesting history. So, but the story began with Beck. What does Beck do? At this time, 1925, there was already since a couple of years a class of solutions to Einstein's field equation known, which have been found by Hermann Weyl, and this was the class of axisymmetric, static vacuum solutions. To Einstein's equation, Einstein's field equation. Yeah, this general class of solution, the general equations which govern this class was found by Hermann Weyl already in 1917. So was found by Hermann Weyl, famous German mathematician who made very important early contributions to general relativity in 1917. And what Beck did was he just took this class of solution and he changed the character of the coordinates so that instead of axisymmetric and static solutions, he got cylindrical symmetric but non-static solutions. So what is an axisymmetric static solution? So we had Weyl coordinates. So these are called Weyl canonical coordinates, the coordinates in which these solutions are written. So this is a time coordinate, it's a cylindrical radius coordinate, an angle coordinate, and the z coordinate. So these are cylindrical polars. Yeah? So rho is the distance from the z-axis, phi is the usual azimuthal angle, and z is the z coordinate as we always consider. And what does axisymmetric and static mean? So the metric must be independent of t. Yeah, it should be not time dependent, and it should also independent of phi. It should not depend on this angle phi. This is not yet axisymmetric and static. This is what one calls axisymmetric and stationary, because what is still allowed is that the whole thing rotates along the axis. Yeah? Then it would also be time independent if it rotates with a constant angular velocity. And it would also be axisymmetric because no position of the phi coordinate is distinguished, right, if it is rotating. So if you want to exclude the rotating case, then and that's what one calls a static metric. And then you require that it is invariant with respect to a change of the phi coordinate to minus phi. Yeah? If you change phi into minus phi and you have a rotating solution, then it rotates backward and you see the difference. Yeah? So a rotating solution would not be invariant under such a transformation. But if it's just static, if it's just sitting there, not rotating, then it doesn't see such a transformation. So this is these are the symmetry assumptions which are put into this metric, and then while express the general form of the metric with the symmetry in a convenient form. So we use the freedom of changing coordinates to reduce the number of metric coefficients as far as possible. And then he inserted this into the vacuum field equation, and he discussed in detail the system of differential equations. So this was known in 1925 when Beck started his work. And what Beck now did was that he just interchanged, roughly speaking, the t and the z coordinate. Yeah? Here we have something which is time independent, but there's no translational symmetry in the z direction. If I interchange the t and the z, then the whole thing becomes time dependent, so it may describe waves, but now it is translation invariant in the z direction. And we have to be careful because t is a spatial coordinate and z is a time coordinate. So what Beck did, Beck transformed, so roughly speaking, he transformed t into z. Well, first of all, they have different dimension. So let's put a c here. Then both have the dimension of a length. Then it works better. And this would make a time coordinate, this would make the spatial coordinate z into a spatial coordinate t. So in order to have the causal character preserved, that z should be a spatial coordinate and t a temporal coordinate, he put an I there, which doesn't make any problem for Einstein's field equation. Yeah? Purely formally, you can insert complex numbers into Einstein's field equation. There's nothing going wrong with the equations. And if in the end the metric which comes out is a real metric, which will be the case here because this occurs only quadratically, then everything is fine. And of course the same thing that also goes into ICT. Yeah? So with this transformation, applied to the general form of this Weil metric, Beck arrived at a metric which is now axisymmetric and translational invariant in the z direction. So it has cylinder symmetry, but it is time dependent in general. And so what resulted was made the following form of the metric. So the metric coefficients are named in the same way as they were named by Weil in his case. So he retained this notation for the coefficients. So there's a function gamma and a function psi. Both depend on t and rho. I'll write this in a minute. B rho squared minus c squared dt squared plus e to the minus 2 psi v squared. This is another metric coefficient function, w, which is also dependent on rho and phi, d phi squared, and plus e to the 2 psi dz squared. And with gamma, psi, and w depending on, well, in the Weil case, they were depending on rho and z. Yeah, these were the coordinates with respect to which I have no symmetry. Now I have z replaced by t, so they must depend on rho and t. Yeah? So these are the two coordinates with respect to which I have no symmetry. So you see the metric coefficients are independent on phi and on z. So this reflects cylindrical symmetry. So, okay, let's have a look at this metric. So obviously there are no cross terms which involve a d phi. So there's no term d phi dz, d phi dt, or d phi d rho. Why not? Because this symmetry is required. Yeah? Such a term would violate this symmetry. Then there is the diagonal terms proportional to d rho squared and dt squared are in this form. So they come, d rho squared and c squared dt squared have the same coefficient. Why is it possible to choose the coordinates in such a way? Well, this is a two-dimensional metric. Yeah, the surface parameterized by rho and t carries a two-dimensional Lorentzian metric, and every two-dimensional Lorentzian metric is conformally flat. It may be written as this flat metric times a factor. Yeah, that's a general property of two-dimensional metrics. So this is used here, and then we have no other cross terms. No cross term. What is still left? Cross terms which involves a z. And what Weil had shown was that they can be killed by an appropriate coordinate transformation. Yeah, I will not do this here in detail. So this is really the general form of a metric with the required symmetries. So originally done by Hermann Weil for the case that here instead of t I have the z, and now with this transformation rewritten by Beck in this form. So every cylindrically symmetric spacetime can be written in this form. Yeah? And this is, these coordinates are also in this case, they are called the canonical Weil coordinates, or the analog of canonical Weil coordinates for this time-dependent case. Okay, and now one has to plug this into Einstein's field equation, this ansatz. It's a little bit more complicated than for the Brinkmann waves. For the Brinkmann waves, it's quick. It's not a big deal. Here one has to calculate a little bit, and I don't want to do this on the board. So in the end, you get 5 differential equations. Yeah. So let's recall Einstein's vacuum field equation. In general, these are 10 differential equations, right? It's symmetric, and we have 4 dimensions. So a symmetric 4x4 matrix has 10 components. So it's a system of 10 differential equations. The more symmetries you have, the less equations survive. Yeah? And here we have some symmetries still left. And for this reason, we get only 5 differential equations. In the case of the Brinkmann solution, we got only 1 equation. Yeah, you see Brinkmann is much simpler. So inserting into r mu nu equals 0 yields 5 equations. And I write them down now. So of course, there are differential equations for these coefficients. I forgot to say a word about this. So you see, I explained why certain combinations are missing. Yeah, why there's no d phi dt term and so on. So we have only this term, and this term, and now coefficients. And you can give any name to these coefficients you like. So this coefficient here was called e to the 2 psi. This already guarantees that it is positive, so that z is really a spatial coordinate. Then this here will have a different coefficient, and you can write this as e to the minus 2 psi with a new function w. Yeah, that's always possible. So this defines then the new function w. And why do you write it in this way? Well, because then Einstein's field equation becomes particularly convenient. So then you have the psi and the w. And this is another new coefficient. So it's convenient to split off the factor e to the minus 2 psi. And what is left is called e to the 2 gamma. So these three functions are just convenient labelings for these 3 coefficients. Yeah? So you could have called this A, this B, and this C. But then you would have seen that Einstein's field equation doesn't become so nice as it becomes with this labeling introduced by Hermann Weil. So I now write down the 5 equations. Of course, it's second-order differential equations for the three functions gamma, psi, and w. Begin with w. 1 over c squared t squared w is 0. Kind of a wave equation for w, right? So let's call this b1. I'm not sure why I used b. Maybe for back, yes. Then d2 rho psi minus 1 over c squared dt squared psi plus d rho w over w d rho psi minus tw c squared w dt psi is 0. This is b2. These two equations come from the zz and the phi component of this here. Yeah? So you write down the zz component and the phi component, and you combine these two equations in a new way. Then you get these two equations. Then the next one is second time derivative of w, 2c squared w plus d rho squared w over 2w minus d rho w d rho gamma minus dt w c squared w dt gamma plus 1 over c squared dt psi squared plus d rho psi squared is 0. That's b3. And b4 is shorter, and before b5 also d rho squared gamma minus 1 over c squared dt squared gamma. Always these wave operators occur, right? 1 over c squared dt psi squared plus d rho psi squared is 0. And the last one. So these come from the rho and the tt components. These two. Yeah. If you write the rho component of the field equation and the tt component, and you subtract them and you add them or something like that, you get these two equations. And then there is one equation left. This is the only one with mixed derivatives. D rho dt w minus d rho w divided by w dt gamma minus dt w over w d rho gamma plus 2 d rho psi dt psi is 0. b5. Okay. And now you look at this for a couple of hours and you think about how to solve this system of differential equation. Of course, everything would be much simpler if instead of the three functions, rho, psi, gamma, psi, and w, you would have only two. And so the first question, actually this was done by Weil already in his case. The first question which was investigated was, is it possible to specify one of these three functions, for instance, by identifying it with one of the coordinates? And actually that's possible. Namely, the w can be identified with a coordinate rho. So we can make a particular coordinate transformation so that in the new coordinates, the w becomes just the rho coordinate, and then the system simplifies considerably. Actually, this is true not in general. The function w must satisfy a particular condition. So you have to distinguish several cases. And this is the case which, if we talk about Beck or Einstein-Rosen waves, which is the most important special case, this is a case when the gradient of w is space-like. Oops. So we will assume this and then solve the system under this condition. And then I will make a few remarks about the other cases, but not do the other cases in detail. So this is case A. Let's see. So let's assume that the gradient of W is, let me see, space-like, yes. So this is d rho W squared minus 1 over C squared dt W squared is bigger than 0. Yeah, of course, this need not be the case. Yeah, it's a particular case, and we consider this case first. Yeah, actually, this is this is the Euclidean gradient, right? But if you look at the form of the metric, you see that this is also up to an exponential function, which is non-negative. It is also the gradient with respect to the physical metric. So it really means that the gradient of W is space-like. So if this is true, then of course the gradient is in particular different from 0. Yeah? So if this is bigger than 0, then it's in particular not equal to 0. So this means that I can use the function W as a coordinate. Yeah? If not every function can be used as a coordinate because the differential of a coordinate is not allowed to have a 0, right? If the differential of a coordinate would have a 0, then this coordinate system would break down at this point. Yeah? Then the 4 coordinates lines would no longer intersect each other under an angle different from 0. So you can use a function only as a coordinate if its gradient is non-zero. But this is here true by assumption. So then we can choose. We can use rho tilde, which is W of t and rho, as a new coordinate. Okay, if I change the rho, then probably it's a good idea also to change the t. So the question is, how do we change the t? Oops. And I write this condition in terms of its differential. So we make a coordinate transformation. So you see, if we succeed in doing this and then write everything in the new coordinates, then where we had the function W before, then we have the new rho coordinate. And that's what I said while I erased the board, that we make a coordinate transformation that the W becomes a new rho coordinate, right? And then, of course, the system of differential equation simplifies considerably. So make coordinate transformation. So our old coordinates have been t, rho, phi, and z. So I now go to a t tilde, a rho tilde, a phi, and a z, such that the following. So phi and z are unchanged. So the d rho tilde obviously should be given by this expression. So I just take the derivative of the right-hand side. So this is dt rho dt plus d rho w d rho. Yeah, this is just this here differentiated. So that's the relation I want to have. And then I have to tell you how the new time coordinate should be defined. I write something down and then I prove that this is in fact possible. So I want to have this equal to the rho w dt plus the tw c squared d rho. And now question to the audience, is this always possible? So does a coordinate t tilde always, a function t tilde always exist so that this equation holds? Or is there maybe an obstruction against this, which we have to check? Question to the audience. Is every expression of this form a differential of something? Obviously not, because if it is a differential, then this here must be the t derivative of t tilde, and this must be the rho derivative of t tilde. And partial derivatives commute. So if I take the t derivative of this, I have to get the same thing if I take the rho derivative of this. So I have to check, is the rho derivative of this here the same as the t derivative of this? Then such a function t tilde really exists. Otherwise it does not exist. That's what one calls an integrability condition. Yeah? I have to check this. And integrability condition satisfied. So let's check this. So I have d rho dt t tilde has of course to be the same as dt d rho t tilde. So if I insert this, rho derivative of this, is this the t derivative of this? And now look at Einstein's field equation. There are the 5 components, and, well, just the first one, B1, is precisely this integrability condition. Yeah? So if we want to solve, say, not the vacuum field equation, but the field equation with a certain energy momentum tensor with this metric ansatz, then this transformation is not possible. Yeah? But for the vacuum field equation, it is possible. So this is in fact, so this is true because of B1. Because of B1. So such a coordinate transformation exists indeed. So, so our new coordinates now, so we have now the new coordinates rho tilde and t tilde. So actually I cannot really integrate out the t tilde. I cannot write t tilde is equal to and then write this function explicitly, this function of rho and t, but I know that such a function exists. Yeah? It is given in terms of its derivative. So then, let's see what happens with our metric. In the metric we have this expression d rho square minus c squared dt squared. Let's see, wow, this looks after the transformation, minus c squared dt tilde squared. Let's see what this is. So I just have to insert these expressions. So the rho squared is what? It is dt w dt plus the rho w d rho, everything squared, and minus c squared, and then this, no, this thing here, squared, dtw, dt squared, this here squared, d rho w dt, plus dtw over c squared d rho. Is true with the squares here? Let me see. Yes, I think it's true. The c squared should be correct. Let me see if it works out. So then I have what? I have, in front of the dt squared, I have dtw squared minus c squared d rho w squared. So this comes in front of the dt squared. And it also comes, what comes in front of the d rho squared? The same thing, but divided by c squared, right? Minus 1 over c squared d rho squared. Let's see if this is true. These two terms, this is this here. Minus times minus gives plus. And these two terms, this is this here. dt, I get a 1 over c squared. Yes, yes, it's true. I think that's true. And the other two, okay, this is, these are the d rho dt terms, the mixed terms. So where I multiply this out, I get 2 times dt w, d rho w, dt d rho. And here I get the same thing. C squared cancels against c squared, so I'm already done. Yeah? So we see that that's the expression which we have Yeah, maybe I should have multiplied by c squared. Looks nicer, right? Or is the sign wrong? Let me see. D rho squared. Okay, let me. Yeah, let me divide this by minus c squared, and this multiply by minus c squared. Divide by minus c squared. Then I get d rho w squared minus 1 over c squared. No, it's, yeah, 1 over c squared dtw squared. And here I multiply with minus c squared, then I have d rho squared minus c squared dt squared. That's nicer. So you see here I have this expression, here I have this expression without the tilde. So that was the transformation behavior I wanted to get. So we see that, yes, and what is important, this here is positive by assumption. So this was our assumption. Until now I have only used that it is non-zero. Yeah, that the gradient is non-zero. But now I use that its Lorentz length is really bigger than 0. So I want to replace in the first term d rho squared minus c squared dt squared. I want to replace this with the twiddled expressions. So then, of course, I get this unwanted factor, but I can integrate this in the factor e to the 2 gamma minus 2 psi. So I introduce, I call it gamma tilde and psi tilde, I think. Well, I have to introduce it in only one term, say in the gamma. E to the 2 gamma tilde is e to the 2 gamma divided by this term, which is non-zero. D rho w squared minus 1 over c squared tw squared. So if I multiply these two terms together, then I see that this drops out, and I get just e to the 2 gamma times this term d rho squared minus c squared dt squared, which I have there. So then the metric becomes the following form. Okay. So I have e to the 2 gamma tilde now, minus 2 psi. I haven't done anything with the factor e to the minus 2 psi. Instead of d rho squared, I have d rho tilde squared, c squared dt tilde squared. So this is the first term up there. Yeah? So what I've written here is e to the minus 2 psi times the two left-hand side multiplied together. And this gives e to the minus 2 psi, the two right-hand sides multiplied together. And this is exactly what we have there on the right-hand side. These two right-hand sides together. Okay, that's the first term, and the other terms I copy, right? Yes, I copy. Plus e to the minus 2 psi. Ah, there's w. W, of course, is now, w is rho tilde. Yeah, rho tilde squared. Yes, d phi squared. And cannot do anything with this. 2 psi dz squared. So that's the form of the metric. So you see, if I now drop the tildes, if I say my new coordinates are now the coordinates which I use from now on, then I see I get the same form from which I started, but instead of the w, I just have the rho. Yeah? So what I've shown here is that if the vacuum field equation holds, then this coefficient w can be identified with the coordinate rho. I can choose the coordinate rho such that this is the same. So now I drop the tildes and continue with this expression. So then the 5 equations which I have to solve are still true, but instead of w, now I have the rho. Yeah? And then the equations become considerably simpler. So I think I write them here on the left-hand part of the board. And we will then go on solving these equations. Oops. So all this was worked by Hermann Weyl. Yeah. So what Beck had to do was just making this transformation with the imaginary unit, and then he was done immediately. Everything carried over. Okay. So let's begin with B1. You see, B1 is identically satisfied. If W is rho, then the first derivative gives a 1, and the second derivative gives a 0. And because W is independent of T now, this is also 0. So B1 is identically satisfied. We can forget about it. So we have only 4 equations. So, oops. So B1 is identically satisfied. Let's see what happens to the other equations. Here I have, well, with the psi I didn't do anything. So I have to copy this. Minus 1 over c squared. T, is this a second derivative or a square? Yeah, you have to be careful not to confuse the first derivative squared with the second derivative. Yeah? Both expressions occur all the time. This is a 1, yeah? Divided by rho, 1 over rho. D rho psi. This is a 0. And on the right-hand side, I also have 0. So this is the new version of B2. So here, this is 0. This is 0. This is 1 over rho, d rho gamma. Well, it's supposed to be a rho. It's probably not readable. D rho gamma. Where am I? Here. Here. 1 over rho, d rho gamma. Yes. This is 0. And this I have to copy. Plus 1 over c squared. This is dt psi squared. Is this really plus d rho psi? I'm a little bit confused. Usually they come with different signs. Let me check if I made a mistake. Oops. No, that's what I have here. So let's see if I... So that's B3 prime, B4 prime. Okay, I think I cannot do anything with this. There's no W involved, right? D rho, what was it? Gamma? Yes. Minus 1 over c squared second time derivative, minus 1 over c squared. dt psi squared plus d rho psi squared. That's B4 prime. And the last one, this is 0, because W is independent of T. This is 1 over rho dt gamma. 1 over rho dt gamma. This is 0, plus 2 rho psi dt psi. 2 d rho psi dt psi equals 0. Okay, And now I have not the slightest idea what to do now. I have to look it up. B2 prime, yes. We look at B2 prime. It is a differential equation for psi alone, yes. Yes, you see, this is a differential equation for psi alone. So we can try solving this with a particular ansatz. No, not this page. Well, actually, this looks very familiar. If you have ever looked at the Laplace equation, the wave equation in cylindrical polar coordinates on flat space, ordinary flat space. If you have a cylindrically symmetric problem, you solve the wave equation. Yeah, that's the time derivative plus the Laplace operator. You see that this, and you assume that the solution is independent of phi and of z, so it depends only on rho. Then you see that these two terms together here, this is just the Laplace operator in cylindrical polar coordinates. Yeah? There are also the terms where you have phi derivatives and z derivatives, but they are in our case, are zero, because the metric, all metric coefficients are independent of phi and 0. So what we have here is just the wave equation in cylindrical polar coordinates for a solution function which depends only on rho and t. And the solution to this is well known. Does anybody know what this is? The solution to the wave equation, or well, of course you can split off the time factor in the usual way. Then you end up with a Laplace equation. Laplace equation in cylindrical polars for the radial coordinate. You know what this differential equation is? Bessel, very good. Yes, it's a Bessel differential equation. And the solution are the Bessel functions. So the solution is well known. So B2 prime is the wave equation, the ordinary wave equation, D'Alembert operator on flat space-time, is a wave equation in cylindrical polars for a function psi which depends only on t and on rho, yeah, independent on the solution. So the solution is where there are these usual time harmonic factors which are introduced in order to get rid of this term, and then you end up with a Laplace equation, and the solution to the Laplace equations are the Bessel function. Solution is given in terms of Bessel functions. Of course, here in Bremen you should know about Bessel. He spent a couple of years here. Not his most fruitful years. Then he later was in Königsberg. That was his great time. But in younger years, he was here in Bremen, and there's a statue, of course. It's this little fountain in the central part of the city near Galleria, right? Okay, so the Bessel functions is given in terms of Bessel functions. So psi of t and rho is what? So there are terms, well, you can either write it in terms of e to the I omega t and e to the minus I omega t, or you can write it in terms of cosine and sine. So you have a term, I've chosen the purely real representation with cosine and sine. And then you get, here in front of this, you get the Bessel function. So an arbitrary coefficient a, the j naught of w and rho, and here you have the y naught of w times rho. So this is the general form of the solution. There are arbitrary coefficients. If you want to have real solutions, that's what you want to have. They have to be real. And these are the Bessel functions. Oops. And for the omega, you can choose any real number you like. Yeah. Oops. So this is the solution. These Bessel functions have the following property. This J naught is, which one is regular at the center? Let me see. So this is called the Bessel functions of the first kind. This is called the Bessel function of the second kind. And the J naught is regular. The J naught is regular. And the other one is becomes singular on the axis. Yeah? And now the question is, do we want to have solutions where we have a singularity on the axis? Yeah? Probably we do not want to have such solutions. That's the reason why we choose the b equal to 0. So y naught has a singularity on the axis. Axis means rho equals 0, right? So for this reason, we choose b equal to 0. So this is regular everywhere. Yeah. So this is well behaved on the axis, and so we have solved this equation. Let me see if yes. Then we have also solved b2 prime, and then we have to continue with the other three equations. And as ever so often, one of them is actually need not to be considered. So what we will do next time is we will solve b3 prime and b5 prime. And one can then show that b4 prime is automatically satisfied. Okay, but I won't manage to do this in 3 minutes. So I think I stop here. So we will solve this, but maybe I can use this remaining 3 minutes for telling a little anecdote about this, this class of solutions. So what we are doing right now is what Beck did in 25. And Einstein and Rosen also did it in 37. When they discussed this solution, they discovered a certain singularity, not this singularity, another singularity. I will talk about this next time. And this led them to the conclusion that actually gravitational waves in the full theory do not exist. Einstein had postulated the existence of gravitational wave in 1916. This is very famous, right? We celebrated this event to greatest extent in the last year. But then in 37, he thought everything which I have done in 1916 was completely wrong. It was an artifact of the linearization. In the full theory, gravitational waves do not exist. And he wrote this paper with Nathan Rosen, and they submitted it to Physical Review. And to his great luck, he found a very good referee. We know today the referee was Robertson, the one from the Robertson-Walker universes, and Robertson detected this error. So he immediately realized that this conclusion was wrong, and he wrote a very detailed, very good referee report in which he explained that this conclusion was wrong. And what happened when Einstein got this referee report was he got extremely angry. It's completely out of character. We usually consider Einstein as a very mild-mannered, very friendly person. He got really rude in this case, because it has never happened to him before that one of his papers was refereed. He didn't know this. When he submitted in Germany a paper to Annalen der Physik, the editor Max Planck immediately accepted it. He never sent it to a referee. And at the academy, of course, he was a member of the Prussian Academy. He presented the paper, and never a referee was involved in this. So it was for the first time in his life with this paper that he got a referee report, and even one who said that the paper should not appear in this form. And he got extremely angry. So he wrote a response letter to the editor. I sent you this paper for publishing, not for sending it to colleagues. Yeah? And I withdraw the paper, and I will never again submit anything to Physical Review. And he did this. Fortunately for him, it was big fortune for him, big luck for him that this paper was rejected, because afterwards he realized that he had made an enormous mistake in this paper. Yeah? And he wrote a new version of the paper. At this time, Rosen was no longer in Princeton. He had moved to Russia. So Einstein wrote it alone, but it appeared under the name of both of them. And the content of the paper was completely different. The content of the first paper was, we have proven that gravitational waves do not exist. The content of the new version was, we have found a new class of gravitational wave solutions. And in this form, the paper is published in a very obscure journal, the Journal of the Franklin Institute. I've never heard about this journal in any other relation. And so this is the revised version of this original. The original paper is lost. We have the correspondence with the editors, but not the original paper. But from the correspondence with the editor, it's quite clear what was in this paper. So in this paper, it was clearly stated that gravitational waves do not exist, which of course is complete nonsense. And well, Einstein realized that he had made a mistake. Actually, he discussed it with Robertson. Robertson came to Princeton. Of course, he didn't tell him that he was a referee, but he discussed this matter with him, and he explained it to him, and then Einstein understood. Rosen never changed his mind. I met Nathan Rosen in 1980. It was my first big GR conference in Jena, and Rosen still was of the opinion that gravitational waves did not exist. Yeah? So everyone in the audience reacted a little bit irritated when he gave his talk, but it was quite clear that he was still, at least very skeptical if gravitational waves existed. He passed away, I think, in the early 90s or so. So he didn't live long enough to see gravitational waves. But Einstein changed his mind completely. So he after a few months, he realized that he had made a mistake and that gravitational waves do exist. So this is this rather famous story about this Einstein-Rosen paper. And what is also important, what I've stressed here, is that the whole calculation and the correct interpretation of these solutions was given 12 years earlier by Beck. The Beck paper is an excellent paper. Yeah? It's quite clear, and all the interpretations are given in great detail. It's a very good paper, and one really should call these metrics Beck-Einstein-Rosen solutions. Okay, so I think I stop here. I continue this calculation next time. I think it will take me, certainly not 1.5 hours. And then I have to see what I do in the remaining time. Originally, I planned also to talk a little bit about the Robinson-Trautmann solutions. Maybe I do this, or otherwise, if you have questions, we can just end with a round of questions. So we decide this on Friday. Yeah? Okay, see you on Friday.